Hi everyone, we are Team Seek Deep and we are Apurva, Chandni and Roshni and our project is FireSense Predicting Wildfire Risk with Sensor Data. This is a problem statement where we are going to use data and to analysis on it to enhance early detection and mitigation efforts, significantly reducing wildfire risk. It's a business purpose and this is a business use case. I would like to go on to the collab structure. I mean, all the collabs that we have over here. So here, if you see all of the collabs that we have done in this project are here, all of the weeks. And then after that, we also have the data sets in their particular week folders. And then for the last sixth week, I think we used the same week 5 data set, so we didn't create another one for that. And then here we have all the other links. So I would like to start with our first assignment. So yeah, this is the clustering on wildfire prediction. And then first thing we're doing is we're getting the data set as wildfire local, and then we're reading it over here. Then we're displaying the first few rows. All of this is just the EDA we're doing. And then this is all of the cleaning that we're doing. We're filling the null values, replacing, etc. And then here we're using the min-max scaler to keep the values between 0 and 1. So it's nothing but we're just normalizing them. And then here we are applying the k-means clustering and then we're visualizing the clusters. So we've used two clusters over here as you can see. And then we got two clusters. And then after that, we just plotted the other graphs like the LST, thermodynamics, and the NDVI, which are nothing but the three columns in our data set. And then this is a correlation heat map that we plotted between all of the uh, variables that we have in our columns. And then here we tested the k-means with different values of k and computed the silhouette scores for that. So we took the range from 2 to 7, and then we just checked what is the correct cluster we should be taking. And then optimal values we printed all of that. So since here the silhouette score was higher for cluster number k is equal to 3, we just took that and we did the k means again. And then we displayed all of that into a table over here. And then this is the visualization for that. And then after that, we did a lot of visualizations over here. So this is a 3D k means clustering results. And then here, this was the PCA that we were doing. We did agglomerative clustering over here. And then this is the second part of the assignment where one of our other teammates had to continue. So this is that. This is nothing but we're just loading the data set again. And then we're doing different box plots and then scatter plots and then also a Widen plot for the NDY distribution. And then here we're doing the k-means clustering and also the DB scan. And also PCA is done for the visualization. And then we're just plotting the clusters. And then this is for the testing part where we're splitting all of it. And then this is the autoencoder. Training the autoencoder, extracting them, and then applying DB scan on the encoded representations. So let's just look at all of the visualizations quickly. So these are all the box plots, and this is a Widen plot. And then this is the actual k-means clustering where we got three different clusters. And then this is the autoencoding feature that we did with the DB scan. So that is that. And this is the third part of the assignment where we have to do k-means with another different clustering algorithm. So the same thing, getting the data set, and then yeah, visualization, all the plotting, all of the. I think this is the same thing. Yeah, let me just skip this. Yeah, so this is the third part of the assignment where we're loading the data set again, and then this is the encoding that we're doing, and then the correlation matrix as you can see, and then feature engineering, and then standardizing the features. So this is where we start with the clustering part. So first thing we did was k-means. We used k-means, and then the second clustering algorithm that we did was optics. So this is silhouette score and also the Dave's Boolean score. So with k-means clustering, these are the four clusters that we got, and then this is using the optics clustering. So this is all about the first week assignment where we worked upon different types of clustering algorithms. So each one of us took k-means as the common algorithm and then another algorithm, whatever we wanted. So in total, we have six algorithms here. three of them being k-means, the other ones are like different optics, TV scan, and agglomerative. So I would like to move on to the second week assignment where we did fractal clustering. So here, this is what we did. The first thing we did was loading the data set, so which is coming from our Google Drive, as you can see. And then we're checking the missing values. And then resampling of the data is done here, where we converted date column to date time, and then a few other things where we did all of this. And then this is the EDA part where we're just describing all of the data that we have. And then this is the visualization of separate columns that we have. So how, like, what all distributions are there, what all columns of uh, are there. And then this is what we concurred from that. Hotter areas with high temperature and sunshine hours are more wildfire prone and all of that. So these are a few things that we got. And then this is a correlation map, heat map that we got from all of the variables that we have. So yeah, this is how we got that. And then these are all the trends over time, precipitation and the temperature. And then this we're just using the standard scaler and then just scaling all of the values that we have. And then yeah, this is the first iteration where we're doing the fractal clustering. And then so we just computed the SSE and silhouette scores for all of the clusters in the range of 2 to 25 just to check what is the correct value of the clusters to be divided. And then you can see both of the graphs, the SSE and the silhouette. And then based on that, I think we decided upon 5, k is equal to 5. And then, sorry, this is the first iteration where we took k is equal to 5. And then we did the first iteration. And we have two other variables that we added over here. So as you can see, all of the clustering is done. And then we got 5 clusters, out of which we took the fourth cluster as the next part for reclustering, so that it has, because it has high FRS and then high FSS risk and the severity. So we took that. And then we're just doing the plotting for whatever we got. So this is the write up for why we chose the fourth cluster, why we chose fourth cluster. And then in that, so if you can see, we took k is equal to 4, and then, sorry, the cluster is equal to 4, and then we again did the k means clustering on that. So this is the second iteration, I would say. So in the second iteration, as you can see, these are all the SSE and the silhouette score values that we got. And then here we were confused between 2 and 6, so that is why we compared values of both of them. So as you can see, 2 and 6, and then we plot the graphs for that. And then we decided upon using k is equal to 6 because it provides a much detailed breakdown of risk levels. Yeah, this is about that. And then we have all the 6 clusters here, and then just displaying all of the values. And then inside this, we again want to divide it. So we just checked which was the next cluster we should have we should be taking. So exact data points belong to subcluster 3 and subcluster 1 for deeper analysis. That is what we did. And then we just computed the silhouette score and the SSE. So as you can see, we chose subcluster 0 as our golden cluster because it has the highest fire risk score and also the most burnt area. So we can conclude saying that subcluster 1 was our golden cluster, which we did save. Yeah, this is all about the week 2 version 1. And then in the version 2, we did the same thing, but we had to add a few extra things. So let me just go to that. So yeah, this is all about the golden cluster. And then, yeah, we saved it. And then after that, we did EDA on that golden cluster. And then all of the distributions that were there in the golden cluster. So this is all about that, and also the correlation matrix. correlation map, and then after that we did the extra credit work. So the first thing that we had to do was um, use Euclidean distance. So instead of using Euclidean distance, we had to use fractal distance using some other formula. So we did Hausdorff fractal distance to compute the k-means. So this is the code that we have for that. So all of this is the code for using Hausdorff. And then we got the final fractal shape, which is nothing but 10,988, 4. So this is for using the other distance instead of Euclidean. And then the second part of the extra credit work was to analyze data distribution for choosing the best algorithm. So this is what we did. So we just did the data distribution, and then we compared we took 4 different algorithms and we checked with that. So as you can see, these are the silhouette scores that we got. And then we took a few other algorithms just to be sure. So as you can see, these are our scores. So out of this, I think the highest we got was mean shift. So that was concluded as the best clustering algorithm. And then we applied mean shift to do the fractal clustering. So this is the level 1 mean shift clustering, and then number of clusters we got here, and then FRS, FSS, we did all of this. And then these are all the scores, SSE and the silhouette score. And then we just check the high risk clusters, whatever are there, like what in which clusters they are there. And then out of that, we chose cluster 0. And then on cluster 0, we again did the subcluster fractal clustering, like division thing that we did. And then again, you can see all of these are the subclusters that we got. And then this is the plot that we have for all the clusters. So best subcluster for fractal reclustering is subcluster 1, because it has high values of both FRS and FSS. And then we just have another option of using 0 or 3. And then, yeah, this is just the EDA that we're doing. How many clusters have how many records, and then all of that. And then this is the level 3 of that. So on that 0, we took we took that as the main cluster and divided that again. So after doing that, these are the clusters that we got. So as you can see, after doing this, we took subcluster 1 from level 3 as the golden cluster. So this is just a write-up for why we didn't choose a few of the things. So yeah, this is all about um, the week 1 and the week 2 tasks. Now my friend Roshni will take over.
Okay. Hello, my name is Roshni, and moving on to the week 3 assignment. So initially, we have 3 datasets, where the primary one is the government wildfire records and the climate data. And for the secondary dataset, we scraped it from the real-time climate and weather data from APIs such as NASA or OpenWeather. And for our third dataset, it is a synthetic dataset we extracted from our golden cluster from the previous experiment. So moving on to the collab, we have installed the necessary libraries and then dropped some of the columns and selected our relevant features. And we have performing the classification on dataset 1. So if you can see here, the random forest accuracy is 86%, and similarly we have tried computing accuracy for some other models too, such as logistic regression and the gradient boosting model, and the SVM, and also the KNN model. And also, yeah, so after comparing all the models, we have seen the observation that random forest and XGBoost has got the most accuracy. And then for the second section of our collab, we are doing the classification on DS1 plus DS2. So similarly, we have computed the accuracies for all the six algorithms here, and then plotted the graphs where the similar thing happened, where the random boost and the XGBoost showed the most accuracy. And similarly, we are amalgamating our all of the 3 data sets here. We are concatenating them, and also calculating all the 6 algorithms accuracy, and also confirm that random forest and XGBoost has shown the most accuracy here. So after that, later we have performed a Muller loop, where it is a systematic process used to evaluate the impact of incremental data amalgamation on model performance. So we're actually evaluating the performance on each iteration, which such as DS1, and the next stage is DS1 plus DS2, and the next stage is DS1 plus 2 plus 3. So computing all the models with the accuracy, we have seen that for the DS1 and for each step of the process, we found that random forest and the XGBoost has shown the most accuracy, and the logistic regression remains stable with little performance change. And also the SVM, KNN, and gradient boosting improved moderately with as more data got added in it. And later we've also printed some visualizations here to actually assess the performance of each stage of the data sets. And then we've also calculated that the best performing model at each amalgamation stage, where it has always been random forest, and also calculated the accuracy improvement with each amalgamation stage. And then we've also visualized our classification report for random forest on all the data sets, for all stages of the data sets, and also plotted some confusion matrix, and also calculated a model performance with more visualizations, and also printed a heat map, and also the accuracy trend as data sets were merged. Yeah, thank you. So my friend will continue the other week's assignments.
Hi all, I am Chandni. In the week 4 assignment, we have taken 2 datasets and we did feature importance and amalgamation of them. And also we found some latent features which are the hidden patterns in the existing columns. Based on that, how a model can improve its accuracy based on that features, we can go through it now. First of all, we are getting the data set and we do some EDA by checking null values and all. And then we are selecting only numerical columns for principal component analysis. It is used to change the high dimensional data into low dimensional data. Here I have visualized a PCA over it, and then I have we have developed tsni visualization here, and we can see here we have created 2 new tsni components, and then we have added those 2 tsni components to the original dataset, and we have checked available columns before the feature selection, and then we have selecting the features based on the random forest ranking, whichever ranks more better, we can take that feature important that features to the model, and then we are testing and training over that model. Then we have taken the keras models or like sequential, and we have taken as dense layers, and define the MLB model and compiling and training the model. Here you can see the graph over here. And then we have taken the linear regression and trained and predicted on the testing data set. We got some values, and we did random forest as well, KNN as well, XGBoost as well. And then we plotted the data here, and then we have plotted the distribution of models in the next cell. Yeah, and then we have done the classification and got the confusion matrix, accuracy, recall, F1 score, and support over here. We did random forest, KNN classifier, and MLP as well in this, and we have plotted the AUC ROC curve for the fire classification, and we got the statistics for all of this. You can see in the below table here. Yeah, this table here shows that we can get the difference between the logistic regression, random forest, and KNN and MLP neural network. These 4 models we did, and at last we printed out the model performance across different classification metrics on the dataset one. So this is all about dataset one, feature importance and amalgamation. Let's move to dataset 1 and 2, feature importance and amalgamation, how we did and all. So first of all, we have taken the dataset 1 and combined with data 2, and then we have downloaded it from the drive over here, and we did some EDA. Then we have done some standardization techniques, and we have applied tsni like before, and we have added two main features and got some values over here. We have plotted the histogram plot in feature importance using random forest. So whichever got more importance, we have taken that. So here you can see tsni1 GSI occurs and tsni2 humid has more importance. So we have taken to process the model, and we are doing regression with these latent features, and we have done linear regression, KNN neighbor, random forest, XGBoost regressor over here, and you can see the MLP training loss for the MLP and actual and predicted values, and also the mean square error and R square error as it is the regression techniques. And we have plotted the error distribution of the models over here, and then in the classification with latent variables, we have plotted the feature importance using random forest, and whichever has more importance, we have taken that features and process those features to the model. So for the classification, we have taken KNN classifier, random forest classifier, and MLP. Mm, so here also we have taken the confusion matrix, precision, recall, F1 score, and support. Compared to previous one, the model with the latent features accuracy got somewhat increased. But here we have plotted the metrics as well, and we have plotted the actual and predicted values in the graph below. Random forest, XGBoost, KNN, and below linear regression. So we have plotted this graph here, and also error distribution of the models and label encoder. So we have for above we did for normal features without latent. These are with latent. At last you can see with latent features and without latent features classification techniques. At last we can see the table of the comparison, seeing the model's accuracy and recall between uh, the features and features with latent features at last. Yeah, this is the comparison. Here you can see columns with latent features accuracy is more compared to columns without latent features. So coming to week 5 assignment, here also we performed principal component analysis along with tsni to increase the accuracy between data sets. So here you can see we have downloaded the data and checked some null values and did some analysis over that. And we have taken the principal component analysis, standard scalar, and then we did a random forest regressor and plotted the feature importance. Whichever have the more importance, we have taken those selected features, and we have split the data into training and testing data set, and we are defining the MLP model over here, compiling and training, and then training loss over here. We have taken linear regression, random forest regressor, KNN regressor, and XGBoost regressor. We have plotted the graphs and got the values like 21.8 to 717 and all. So higher the error, lower the performance. So whichever got the low error, that will be the better. So here you can see the mean square error is low for XGBoost, so it performs very well for that. And then we applied tsni. So we have taken two columns, and then we did feature importance again, and with that tsni features, which means latent features. And then again we did the same for all techniques we have applied to that with latent features. So here you can see the model predicts mean square error and R square error with latent features and without latent features. And then yeah, here you can see the graph with latent features, the error got decreased. and without latent features, the error got increased. And we are combining the both the data sets for the comparison here. And then we did classification for with latent features and without latent features. We did AUC, RUC curves and t-SNE visualizations over here. And random forest, we applied random forest regressor. We did KNN classifier, random forest classifier, sequential and dense layer for MLP. And all we did IOC, ROC curves and find out the confusion matrix, a precision recall F1 score. So here also you can see there is an increase of accuracy for the data with latent features. That means it adds more quality to the data. So at last, you can see the comparison of accuracy with and without latent features at last. So it tells that the data with latent features has more accuracy, and it finds more hidden patterns to get more accurate results. Over to you. Over to my friend.
Moving on to our week 6 assignment, which is a wildfire cost classification with pre-processing and resampling and also visualization. So the first stage of the assignment is to install the packages like scikit-learn and XGBoost and matplotlib. And then in the second part, we are doing our data pre-processing, where we are loading our data and also dropping the irrelevant columns like date and fire name, and also encodes county and the target variable cause. And then we're standardizing and also splitting our data into testing and training. And then later we are getting our feature importance by plotting our gneat importance. So where these are the importance values for each feature. And later we are going ahead with our classification with multiple models, and before that we are applying smooth analysis for upsampling, and also adding some grid lines and improving the aesthetics for the features. And this is the graph for that, and also applying random undersampling, converting them into data frames, and also performing the downsampling. Where the downsampling is completed. And then we are doing our classification with multiple models, where we are training and evaluating 4 models, which is the random forest, SVM, and XGBoost, and also the MLP classifier. And then here each model also includes training on the training set, and also evaluation with the confusion matrix classification report, and also our F1 score. As you can see, we have printed our confusion matrix and also the visualizations for all the algorithms. And this is our complete model performance summary. And then later we are going ahead with our class imbalance handling, where we are analyzing class distribution of cause, which is our target variable, and also applying random oversampling and also random undersampling, where the oversampling includes duplicating the minority class samples, where the undersampling involves removing majority class samples. And also we are retraining the classifiers on resampled data sets, and also comparing our F1 scores to check the improvement achieved here. So as you can see, this is our recall F1 score comparison, precision comparison, and also the recall and the specificity. And then we are plotting the distribution for after the upsampling and also after the downsampling. As you can see, we are performing the models at each stage of the process, and also reflecting on our complete model performance summary, where we're also plotting the specificity here. And in the later stages, we are using matplotlib and seaborn to visualize the class distributions before and after the resampling, and also plotting our feature importance, showing our confusion matrix. And then in the stage 6, we are creating a HoloViz dashboard, which is the final stage of the assignment, where we are titling, which is the upsampling and downsampling with humid feature, where though not fully shown yet, this use like a panel, holo views, or plotly for interactive dashboarding to visualize the impact of the humidity on our particular fire costs. Thank you.